Assalamu alaikum wa rahmatullah. This is the second part of the STP, Spanning Tree Protocol class. In part one, we have stopped on the root election process. For this, before we continue with the election process, I just want to remind that we already have taken the spanning tree port rules, which is the designated port rule and the root port rule and the alternate port rule. And I already explained in the first part. The second thing the other thing that we have taken also is the port ID. Port ID is based on what they call it the priority, port priority, and the MAC address together, the combination of these two. So the lower the number is, the higher the priority. The other thing is the timers. Timers, I already explained the message age and also the maximum age. And the message age is going to be increased by 1 every time we travel the packet. The BBDO packet travels through one switch. The value of the age will be increased by 1. And the maximum age will stay as it is. If the maximum age exceeds the, is the message age exceeds the maximum age, then the packet will be discarded. Now we come back to the root election process. So for the STP, actually all switches, all STP enabled switches advertise BBDU to other peers, the other peers with self as root. So at the beginning, the first time we start up the network, all switches will consider themselves the root. So they will generate a BBDU bucket and send it to the other switches to tell them that, hey, I'm the root. Then everybody need to compare the root ID, also to compare the router, the switch priority, every switch need to compare the switch ID and root bridge ID, I mean, and also the priority of the switch. Then based on the information, they can find which one is the root bridge switch. So we will go here through these comments. The spanning tree convergence process is an automated procedure that initiates at the point of switch startup. So all switches at startup assume the rule of root bridge within the switching network. So every switch will assume that itself is the root bridge. So the default behavior of a root bridge is to assign a designated port rule to all port interfaces to enable the forwarding of BBDU via all connected port interfaces. So at the initial stage, when we start up the network, so all switches here, as you can see here, they will assume themselves as a root bridge, all of them. Then every port here will be set to designated, So designated means that the forwarding of BBDU is enabled. So after this, as BBDU are received by peering switches, so every switch will send its own BBDU as a root. Then every switch will receive from neighboring switches their BBDUs. Then the comparison between the information that comes over the BBDU will start. So based on the comparison, the switches will select the highest root ID as the root bridge. So in the event that the received BBDU contains an inferior bridge ID with respect to the root ID, the receiving switch will continue to advertise its own configuration BBDU to the neighboring switches. So if this switch, for example, switch B, receives the BBDO from switch A and switch C, and it finds that switch B ID is higher than switch A and switch C, so switch B in this case will continue as root bridge, then it will continue propagate its own BBDO to the others. And okay, here where the BBDO is superior, the switch will acknowledge the presence of a better candidate for the role of root bridge by ceasing to propagate BBDU in the direction from which the superior BBDU was received. So they will detect which one is the highest. If let's say this one is the highest, switch B, so switch C and switch A will start sending BBDU TCN BBDU to the root bridge. So TCN, if you don't forget, it's the topology change notification BBDU. So the switch will also amend the root ID field of its BBDU to advertise the bridge ID. So at the beginning, we said that every switch will consider itself as the root bridge. So the BBDU that we will send from switch C, it will carry the root bridge ID of the switch C. And the packet sent from here, it will carry the root ID as the switch A. And here from B, it will carry also the root ID of the switch B. But if let's say root B is the highest priority, then switch C and switch A will send their own BBDU that carries the root ID of switch B instead of their own, because switch B is the highest priority. Okay, so that's all about the election process. For the rule establishment, port rule establishment process, so the bridge ID and root path cost are used to elect port rules. So the port rule, which is either D or R or alternate, must be established based on the bridge ID root path cost to decide the mode of the port. So an elected root bridge, once established, will generate configuration BBDU to all other non-root switches. Suppose that this one, switch A, is the root bridge based on the election. So it will start to generate configuration BBDUs, because BBDU, as you remember, we have two types. The first type is that's sent from the root bridge to the non-bridges, which is the configuration BBDU. And the other type is that sent from the downstream to the upstream, which is the TCN, which is the topology change notification. So here, the root bridge will start generating the configuration BBDU to all other non-root switches. The BBDU will carry a root path cost, as I explained in the root path cost. So that will inform downstream switches of the cost to the root to allow for the shortest path to be determined. So if you go here, path cost, if you remember here, we have something called path cost. So this path cost is called root path cost. That means the cost to the root bridge, the cost to the root bridge from a certain point of the topology. So if let's say here at this point, the root RBC is 2000 or 20,000, that means we need to, we will be costed the 20,000 to reach the root bridge. So in here, maybe it will become 40,000, and here is 20,000, here is 40,000, here is another 40,000, because the RBC is cumulative. So every time the root bridge here is 0, So the packet will carry RPC equal to 0. When it arrives here, the 20,000 will be inserted, will be added to the 0. It will become 20,000. Then the RPC will carry the 20,000. It will go here to the other switch. Then this switch will plus the 20,000 again. So the cost here will become 40,000. So that's all. If you remember, we have this path cost standard. So for Huawei devices, they use this standard. And as I explained last time, how or why it's considered highly accurate. So here, where do we stop? We stopped here, I think. Okay. So depends on the value of the RPC at every switch, the situation of the ports or the establishment of the port rule will be decided. So as I explained, the bridge ID and route path cost are used to elect port rules. So port rules will be based on this too. So an elected route bridge, once established, will generate the configuration BBDU to all other non-route switches. The BBDU will carry a route path cost that will inform downstream switches of the cost to the route to allow for shortest path to be determined. This RPC actually is going to be used to calculate or to find where is the cheapest or the shortest path to the route. So the route path cost carried in the BBDU that is generated by the route bridge always has a value of 0. So at the beginning, the RPC that's generated from the route bridge actually will be equal to 0. Then once it reaches another switch, that's a non-bridge switch, so that switch will add or will plus the RPC value that's assigned to it, to the route port cost. Okay, so the route path cost carried in the generated is equal to 0. The receiving downstream switches will then add this cost to the path cost of the port interfaces on which the BBDU was received. So if let's say the BBDU is received from here, so the cost of this interface, the cost of this interface, if let's say the BBDU is received from here that carries the 0 value, so the RPC of this port will be added to the 0 here. It will become 20,000. So if the BBDU is also received from here, then from here the RPC is 0. Then, for example, we added 20,000, as you can see here, 20,000. Then the cost here is 0. The cost for this path is 0, and the cost for this path is 20,000. But if let's say we have another switch here, so this switch will receive another RPC BBDU packet that's coming from the shortest one. So this one actually is going to be used. Why? Because this one is going to be used as R, and this one is going either to be D port or A port, depends on the direction to the route, and depends on other information. So here the cost actually is going to be 20,000. Okay, so based on this information, this switch will know that the nearest or the shortest path to the switch A to the route bridge is this, not this one, because this one is much expensive. This one will cost 40,000, and while this one will cost only 20,000. That's why this will become alternative path, will be the active, and this one is going to be active. This one also going to be active. Okay. Okay. So The receiving downstream switches will then add the cost on which the BBDO was received and from which a switch is able to identify the root port. So based on the information received at the switch B from the port number 1 and the port number 2, the switch B will decide which port is shorter to the root bridge. Then that shorter path the port will be assigned the root port rule. And the other port, it may take D or A, depends on the situation. So in the case where equal root path costs exist on 2 or more LAN segments to the same upstream switches, the port ID is used to discover the port rules. So if let's say we have, for example, if let's say we have 2 paths with the same cost, 2 paths to the root with the same cost. So in this case, the path cost is the same. So in this case, what they call it, the switch port ID. Okay, the switch port ID actually is going to be used to select which one is active and which one is inactive. So if let's say this is the port 3 and this is port number 1, so port number 1 will be R and port number 3 will be A. Okay, that's all about it. Let me go forward to the port state transition. So port state transition actually is in the STB, we have 5 states. We have 5 states of the ports. So the first state is the disabled. So let me read the information below here because we don't want to miss anything. As a part of the root, bridge, and port rule establishment, each switch will progress through a number of port state transition. So the scenario of every port will go through all of these states. So any port that is administratively disabled will be considered to be in the disabled state. So this one is disabled state. So if the port is disabled. So enabling of a port in disabled state will see a state transition to the blocking state. So after we enable any disabled port, so it will go directly to blocking state. Will go directly to blocking state. Then any port considered to be in blocking state is unable to forward. So the blocking state, that means the port cannot forward any information. So BBDUs cannot go through this kind of ports. So unable to forward any user traffic, but is capable of receiving BBDU. So it can receive only the BBU. So blocking means it can listen, but it cannot forward. Then any BBDU received on a port interface in the blocking state will not be used to populate the MAC address table of the switch, but instead to determine whether a transition to the listening state is necessary. So depends on the information when the port is in the blocking, so it can receive the BBDU. Based on the information inside the BBDU, it can decide whether it need to go through to change its state from blocking to listening. So that depends on the information in the BBDU. So if some failure happen, or maybe some active links become disconnected, in this case, maybe a blocking port, it can be translated to listening. Okay, now we go to the listening state and we understand what happened during the listening state. So the listening state enables communication of BBDU information following negotiation of the port rule in step 2. So here, after step 2, after the blocking, if the states is changed from blocking to listening, then the negotiation will happen. So, sorry, the negotiation will happen at the blocking stage, but after that, based on the negotiation, they can decide whether to go to listening state or not. So, but maintains restriction. So still, it's restricted on the populating of the MAC address table to the neighboring information. So in this state also, the port can receive, but it is not going to send any MAC address table to the other neighboring switches. So here is also one way. So blocking and listening are only receiving information, but in the blocking, they can decide whether to go to listening or not. So the next thing is the transition to the blocking state from the listening or other states. So from listening, we can go back also to the blocking. So this state this transition from listening to blocking can happen, may occur in the event that the port is changed to an alternative port rule. So if, let's say, we was in the blocking, then based on the BBDU information, we decided to go to listening to activate the port. Then based on the information, based on priorities, port priorities, costs, and so on, we decided that this port will stay alternative. So it will go back to the blocking state. So the transition between listening to learning, so from listening to learning is another case, and learning to forwarding state. Actually, when we move from listening, it will move to learning. Then after that, it will go to the forwarding state. It greatly dependent on the forward delay timer, which exists to ensure that any propagation of BBDU information to all switches in the spanning tree topology is achievable before the state transition occurs. So the learning state maintains the restriction of user traffic forwarding to ensure prevention of any switching loops. However, allows for the population of the MAC address table throughout the spanning tree topology to ensure a stable switching network. So in the state of learning, the port will listen to the neighboring switches, but also it can send to them its own MAC address table. So it can exchange the MAC address table information to the neighboring switches. But here in the listening and blocking, they can only receive, but they cannot exchange their MAC address table to the neighboring switches. So following a forward delay period, the forwarding state is reached. So after this, if everything goes smooth, after learning, so the state will be transited to forwarding. So here, the disabled state is applicable at any time during the state transition period through manual intervention, the shutdown command. So we, from any state here, as you can see, from blocking, listening, or learning and forwarding, we can go directly to the disabled mode, especially if we interrupt maybe by the shutdown of the port. So it will be moved to the disabled state directly. So that's all about the port state transition. For the root failure actually is considered a topology change, actually. But let us go here. The behavior of the root failure, the scenario of the root failure is different than any failure in the network. So non-root bridges wait for max age before assuming loss of root. So every switch in the topology, which is non-root bridge, they will wait for the maximum age, depends on the maximum age that comes from the BBDU. The last BBDU received from the root bridge will carry the max age. sorry. So based on the max age that's received through the last BBDU, the switches, non-bridge switches, non-root bridge switches, they will wait for the maximum age to expire. If the maximum age expired, for example, if let's say it's 30 seconds, then the switches will wait for 30 seconds. If they receive another BBDU, that's fine. If they cannot receive another BBDU, they have to assume that the root bridge is already failed. So reconvergence is then initiated. So after they detect that the root bridge is failed, then they have to do reconvergence for the topology. So the reconvergence actually is starting after any failure in the network, especially the root failure, and this reconvergence will include the what they call it, the election of a new root bridge. Okay, as you can see here, reconvergence is then initiated, beginning with the root election. So the same scenario will happen, exactly similar to the election that we have taken just now. Events that cause a change in the established spanning tree topology may occur in a variety of ways, for which the spanning tree protocol must react to quickly re-establish a stable and loop-free topology. So from here, we understand that the STP can create a stable and loop-free topology. That means topology without any switching loops. So the failure of the root bridge is a primary example. So this is a primary example of the topology change. Okay, so after the topology change, we have to reconvergence the network. Non-root switches rely on the intermittent pulse of BBDU from the root bridge to maintain their individual root, their individual roots as non-root switches in the STP topology. In the event that the root bridge fails, the downstream switches will fail to receive BBDU from the root bridge, and as such will also cease to propagate any BBDU downstream. The maximum age timer is typically reset to the set value of 20 seconds by default, following the reset of each BBDU downstream. So here the timer actually is going to be reset for the maximum age timer value, for example, the 20 seconds by default, after any reception of BBDU. So after when a switch receives a BBDU from the upstream, then the timer will be reset. So they will wait for another 20 seconds to receive the next BBDU. If the 20 seconds expired and the new BBDU doesn't come, they will assume that the root bridge is failed. With the loss of any BBDU, however, the maximum age timer begins to count down the lifetime for the current BBDU information of each non-root switch based on the maximum age and the message age formula. At the point at which the message age value is greater than the maximum age timer value, the BBDU information received from the root becomes invalid. So if the value of the message age is greater than the maximum age, the bucket will be discarded because they will consider that the information is invalid. And the non-root switches begin to assume that the rule of root bridge will assume the rule of root bridge. So the switches that receives an expired BBDUs, they will start assuming themselves as the root bridge, again, to trigger the election process. So configuration BBDU are again forwarded out of all active interfaces in a bid to discover a new root bridge. The failure of the root bridge invokes a recovery duration of approximately 50 seconds due to the maximum age plus 2 times forward delay convergence period. So from here, we can summarize that the convergence time needed to update or to re-elect a new root bridge, it may take about 50 seconds, which is a very long period for a network. And during this time, the performance of the network will be interrupted. So this is one of the drawbacks or the disadvantages of the normal STP, the legacy or the standard, the first version of the STP. It's very slow to reconvergence. It's very slow to detect or to refresh the topology of the spanning tree and so on. So that's why they came up with something called RSTP, which is the Rapid Spanning Tree Protocol. That's faster than the normal STP. Okay, indirect link failure. So that one actually, this one is considered root failure. But sometimes we will have a link failure. Link failure can be direct and can be indirect. So the first thing we will consider the indirect link failure. So if let's say this link here, this link failed, okay? So this one was the root. This one, it was the root before the link fails. And this one is D, this one is A, as you can see, and here is another R. So if this one is failed, switch B begins root election, but BBDU is ignored by switch C. Why? Because here the switch B will send another BBDU that assumes the switch B as the root bridge. Then the packet will be sent here, but switch C already have the root bridge of the switch A, which is higher priority than the switch B. That's why this packet is going to be discarded. This packet is going to be discarded. Root BBDU is propagated to switch B after maximum age expires. So when this packet is going to be sent here, the new packet for election is sent actually when the BBDU is not coming here. So the delay, the timer already expired, and switch B cannot receive a BBDU from switch A. That's why switch B will assume that switch A already down. Then it will start the re-election process with the switch C, but switch C knows that the switch A is already here. So this packet is going to be discarded, and this is going to interrupt the performance of the network as well. So here we can see, sorry, I've moved to another slide. So in the case of indirect failure, a switch loses connection with the root bridge due to a failure of the port or media. Maybe the link is corrupted, or maybe the port is failed or something like that. Or due to possibility to manual disabling. Maybe manually we disconnect the cable from the port or so on. So of the interface acting as the root port. So the switch itself will become immediately aware of the failure. And since it only receives BBDU from the root in one direction, will assume immediate loss of the root bridge and assert its position as the new root bridge, as I explained just now. So from the example, switch B begins to forward BBDU to switch C to notify of the position of switch B as the new root bridge. However, switch C continues to receive BBDUs from the original root bridge and therefore ignores any BBDU from switch B. The alternate port will begin to age its state through the maximum age timer, since the interface no longer receives BBDU containing the root ID of the root bridge. So here, this alternate port will start the timer. So following the expiry of the maximum age of timer, switch C will change the port rule of the alternate port to that of a designated port. So this one, this port here will become designated. And this port here will change to root. So BBDU from root will come here from this path. So through switch C. So here, it will be changed from alternate to designated port and process to forward BBDU from root towards switch B. So BBDU will start to be forwarded from switch C to switch B, which will cause the switch to concede its assertion as the root bridge and converge its port interface to the rule of root port, as I explained here. So this port will become R. This represents a partial topology failure, however, due to the need to wait for a period equivalent to maximum age plus 2x forward delay. Full recovery of the STP topology requires approximately 50 seconds. As I mentioned in the previous slide, STP is considered very slow because of this thing. So that's why we better move toward the RSB or multiple spanning tree protocols, which is the actually, by the way, is the default of the Huawei devices, the MSTP. So here in this slide, we go to the direct link failure. So in here, we suppose that the failure is this one here. So this port was R and this port was A. And for the, this one is the root bridge. You can confirm that by the states of all ports here set to designated ports. So STP convergence after 2 times forward delay, which is 30 seconds by default. So it could take about 60 seconds. A final scenario involving spanning tree convergence recovery occurs where multiple LAN segments are connected between 2 switches. Actually, this one, I'm not going to read all of these comments here, because this one is much easier than this, the previous scenario, because this one is directly, the failure is directly connected to the root bridge. As you can see, the failure is here, which is directly connected to the root bridge switch. So here the switch will stop receiving the BBDU. So the maximum age will expire. The maximum age timer will expire, and a new BBDU is not going to come. So that's why this port is automatically going to be changed to R for true. So this will be deactivated, and this one is going to be active. So that's all about the direct link failure. So here we are going to see or to understand something called topology change MAC instability. This one actually I already explained before. This can happen when we have what they call it switching loops. If we have switching loops in the network, then the MAC instability will become a common scenario. So this is actually a big issue for switching networks. So changes in the STP topology may invalidate MAC table entries. So based on the change that happens in the topology, maybe because of link failure or maybe because of the root bridge failure or something like that, then the entries in the table is going to be invalidated. So that means some entries will become wrong and they have to be changed by correct or valid entries. So MAC table entries expire only after 300 seconds by default. So if, let's say, some failure happen and some entries become invalid, they will still remain in the table until the 300 seconds expired. So 300 seconds is a big value, which is about 5 minutes. So 5 minutes times 60 seconds is it's 300 seconds. So this is the default value for the expiry of entry. So here, there's a lot of things here. Maybe we need to read. In a convergent spanning tree network, switches maintain a filtered database or MAC address table to manage the propagation of frames through the spanning tree topology. The entries that provide an association between a MAC address, MAC destination, and the forwarding port interface are stored for a finite period of 300 seconds, which is 5 minutes by default. A change in the spanning tree topology, however, means that any existing MAC address table entries are likely to become invalid due to the alteration in the switching path. So therefore must be renewed. So if some entries here become wrong or invalid, then the data may not be able to be delivered to the correct destination. So during this convergence period of time, which is about 5 minutes, the network could be down. So we could lose our connectivity because of this issue. So here they will explain the scenario here, but I'm not going to explain this scenario. It's very clear. So here, if let's say this one actually becomes fail, here if a failure happen, this port actually is going to be disabled, and this switch will no more receive what they call it BBDU from the root bridge. So here, if you can see what they call it, the host here, the host, what they call it, the host A, this MAC address, actually last time it could be accessed from here through switch C through interface 3 here, correct? And this one at this switch, the accessibility to host A is going to be through this interface. So this one is connected to, I mean, saved inside the switching table of switch C here. But this port no more able to deliver requests to this interface. So that's why the packet will be lost here inside the switch until the reconvergence happen and this link become active. When this link become active, it may take 5 minutes to update the switching table here at the switch B and switch C. So during that time, the connectivity between these two PCs will be lost. Okay. Let us go to the next slide, which is the topology change process. Okay, topology change process or topology change notification, which is shortened as TCN, informs route of topology change. So if, let's say, at the downstream switches, there is a failure detected by 1 or 2 switches, this 1 or 2 switches at the downstream flow, they will send a TCN BBDU to the upstream towards the root bridge. They will inform the root bridge that there is a failure, so the root will restructure the spanning tree, to based on the shortest path after the change of the topology. Then the new information or the new spanning tree information is going to be sent back to the downstream switches using configuration BBDU towards the downstream switches to tell them what is the update of the spanning tree topology. So root flushes MAC in trees using BBDU with TC bit set. So here, an additional mechanism must be introduced to handle the MAC entries timeout period issue that results in invalid path entries being maintained following spanning tree convergence. The process implemented is referred to as the topology change notification process and introduces a new form of BBDU to the spanning tree protocol operation. So this is actually to fix the problem of the 5 minutes convergence time of the previous case. This new BBDU is referred to as the TCN BBDU and is distinguished from the original STP configuration BBDU through the setting of the BBDU type value to this one. Because if you go back to the format of the BBDU, you will find one field for the TCN. So if the value that the BBDU type carries the value 0x80, which is equal to 1 to 8 in decimal, so this means that this BBDU is a TCN BBDU, is not a configuration BBDU. So this one, the function of the TCN BBDU is to inform the upstream root bridge of any change in the current topology, thereby allowing the root to send a notification within the configuration BBDU to all downstream switches to reduce the timeout period of MAC address table entries to the equivalent of the forward delay timer, or 15 seconds by default. So here, this process actually is going to minimize the convergence time that's needed in this scenario. So here also although the convergence delay is going to be minimized, but still very slow. Why? Because this one is going to consume about 15 seconds for every hop, about 15 seconds for every hop. So this switch actually is going to be notified during 15 seconds, but this one is going to be notified during 30 seconds. And if, let's say, we have another switch here, this switch will be notified in 45 seconds and so on. So it will waste time, and during this convergence time, the network may become in unstable situation. Okay, the flags field of the configuration BBDU contains 2 fields for topology change and topology change acknowledgement. So we have something called topology change field and another field called topology change acknowledgement. So upon receiving TCN BBDU, the root bridge will generate a BBDU with both the TC and TCA bits set to respectively notify the topology change and to inform the downstream switches that root bridge has received the TCN BBDU. And therefore, transmission of the TCN BBDU should cease. So to summarize this, when a topology change happen here at the downstream, so maybe if, let's say, the failure happened here, this switch is going to send a topology change notification. So when the TCN topology change notification is sent from this switch here to the root bridge, then the root bridge will generate one BBDU that have the what they call it TCA and TC fields. Then this packet is going to be sent here and here, and also will be sent to all downstream switches, as you can see here. So this will help shortening the convergence time. Okay, let me go down here. The TCA bit shall remain active for a period equal to the hello timer, 2 seconds, following which configuration BBDU generated by the root bridge will maintain only the TC bit for a duration of maximum age plus forwarded delay, or 35 seconds by default. So TCA will carry the hello timer, which is 2 seconds, and the what they call it, the TC bit will carry the duration, which is the maximum age plus the forward delay, or equal to 35 seconds. Okay. Topology change MAC refresh. So based on the notification, the topology change notification, in this case, the topology change MAC refresh will happen at every switch to update or to refresh their MAC address tables. So the effect of the TCN BBDU on the topology change process ensures that the root bridge is notified of any failure within the spanning tree topology. So for which the root bridge is able to generate the necessary flags to flash the current MAC address table in trees in each of the switches. So the example demonstrates the results of the topology change process and the impact on the MAC address table. So the entries pertaining to switch B have been flushed, and new updated entries have been discovered, for which it's determined that host B is now reachable via port interface gigabit Ethernet 001. So here if you can see, if let's say this computer here can reach the host B through this path at the beginning, but because of failure that happens here, so this one become invalid or inactive, and this one is activated. So last time inside this switch, we have the path to this MAC address saved here. Is it this one, the cancelled one? The access to this MAC address is going to be through the interface 2, because last time the connection was using this path. But now, because of this failure, the path already changed to this. So accessibility to this host, the same host, host B, is going to be through the interface 001. Okay, this is the topology change MAC refresh. Okay, STP modes. STP modes, actually, here we have in Huawei devices, especially switches that have the number 7. So S37 or S57. So this Huawei switches to which the S5700 series model belongs is capable of supporting three forms of spanning tree protocols. So they have three types of, or three modes of spanning tree. So to change or to set that spanning tree mode, you have to use the STP mode. So as you can see here, if you use STP mode, then question mark, it will show you the help, and you can see the MSTP, RSTP, and the STP. So STP is the first version of the spanning tree protocol. The rapid spanning tree protocol is the improved one, which is the second version, and the third version is the multiple spanning tree protocol, which is the default of the Huawei devices. So in order to change to or to set one of these modes, you have to use the set mode space, for example, STP or RSTP or MSTP, it's up to you. So this is the command to set the mode of the STP. Then actually this command is going to be used from the system view without entering any interface view. Assigning the root. So root can be set manually or by defining the switch as a primary. So if you want to make it dynamic, if you want the root to be elected dynamically, then you can play with the priorities of the switches. So for example here, you can set the STP priority for switch A to be 4096, which is less than the default priority of the other switches, which is 32768 here, and here also 32768. So by this value, by comparing this value to this and this, switch A is going to be elected as the root bridge. Also, if you want to assign without giving or without changing the priority of the switch, you can assign, you can tell your STP protocol that switch C or switch B, I need it to be the root bridge. So using the command STP primary, STP root primary, using this command, we can assign a certain switch as a primary switch, which will become the root bridge switch at the first time. So we have two choices here. The first choice is to play with the priority of the switches, and the second is by using the command STP root primary. So here in this slide, we are going to see how to assign the path cost to a certain switch. So for example, if let's say we are at the switch C and we want to assign a standard for the path cost standard, as you can remember the standards that we have here, this one. So if let's say we need to enable this or that, we have to decide. So 1T is the standard of Huawei. So here, if let's say we want to change to another standard, we can decide using this command STP path cost dash standard. Then we follow by the standard name, as you can see here. Or maybe we hit the question mark to see what are the available standards in the switch. So after we assign or we set the path cost to our switch, then we have to go to every interface and we can manually assign the extra port cost for a certain port. So this one is using the command STP space cost space, for example, 2200 or something like that. So this is to assign cost manually to certain port, and this is to assign a standard of the path cost that's based on the speed of every port. Also here we have the route protection. Route protection actually is only to prevent changes to the topology as a result of route bridge transition caused by receiving higher priority PBTU. Actually this route can be changed, we can have a route bridge transition from switch to another. It can happen based on real network failures, and also it can happen by unauthorized person who wants to hack our network. So if a hacker comes to our network and wants to play with our STP protocol, they can easily install or emulate a switch using a laptop or mobile phone or something like that. They can mimic or emulate a switch, STP switch, that has a higher priority than all of the existing switches in the network. In that case, the hacker device will become the route bridge, and it will receive all of the network traffic easily. And that will interrupt the network. Then it will give the opportunity to the hacker person to read all of the information, maybe to modify them or so on. So that's why the protection of the route bridge is very important. So here, in order to protect what they call it, the route protection, you have to be in the interface view first. You have to decide. You can go to, for example, to switch A and tell the switch A that on interface 001, we want to enable the route protection. That means if we receive from here, if we receive BBDU change, BBDU that wants to change the route, then we have to run the protection algorithm of the route. So route protection prevents changes to the topology as a result of route bridge transition caused by receiving higher priority BBDU. So if the route switch on a network is incorrectly configured or attacked, it may receive a BBDU with a higher priority, and thus the route switch becomes a non-route switch, which causes a change of the network topology. As a result, traffic may be switched from higher speed links to low speed links, causing network congestion. So this is one of the scenarios that may happen. To address this problem, the switch provides the route protection function. The route protection function protects the role of the route switch by retaining the role of the designated port. When the port receives a BBDU with a higher priority, the port stops forwarding packets and turns to the listening state, but it still retains a designated port role if the port does not receive any BBDU with a higher priority for a certain period. The port status is restored from the listening state. So this is how it can protect the route change. So the configured route protection is valid only when the port is designated port and the port maintains the rule. If a port is configured as an edge port, or if a command known as loop protection is enabled on the port, route protection cannot be enabled on the port. So we have either one of them. So either to enable the route protection or the loop protection. We cannot enable the route protection and the loop protection together at the same time. And also this route protection cannot be enabled on edge ports. So that's all about it. to enable the root protection, you can use the STP space root dash protection command, and that's all about it. Here is to display the STP information, and also this one is the continuous slide for the previous one. That's all about it, and that's all about the STP. I hope everything is clear, and inshallah later during the lab we will understand more about it, and inshallah it will be easier. So inshallah I will see you in the next class of the RSTP soon, inshallah. Assalamu alaikum wa rahmatullah.